the diversion type of social stress. It's just because only you plan your shelter that's like yeah. It's not like the other person get like, okay, if every water by this and I'm not as big a distance, how big a triangle, doing this with actual space, they get the gravity and they get grow and it become it's you know, really right routines. I'm gonna make it gym. Now that I make sense. But the more I wake up and gym, I get home, I think so. And I'm a little more patient. So I get sad right now. I also got to collect and cover. And I'm gonna get one more thunder in the breast. I put up my trunk machine. I want to get a neck right here. Actually, I have these two, but I got a I got a cake as well. I haven't seen it here. My homie has so everything else I got. Which video when only came because the thing is, I'm successful. It's a degree because that is not what I mean. In the ball, just when I came, I mean, learning this. So
Like out of the corner of my house, I know.
I'm getting in for shit, and you know,
I don't know if I thought she would have like.
it's just that they don't think
And the guy.
you know, my job was like, it's not hard. Since I can maybe go work at Mohawk, become a fine operator with my experience and be paid 23. If you're gonna Sean, you work for position, but there's really good position Sean will be like 16, 17. If you're secure with the club to eat or ship lead, like you could say like yeah, it's not getting depending on what shift you're doing third shift, you can.
Good morning. All right, in our class, there's something called a pre-test and a post-test. The main purpose is to be able to compare the outcome from both tests to assess collectively how the class design is working for serving our student. So we really want to have some data. Georgia View, if you choose course tools, there's questions in that drop-down menu. I hope that when you have time, try to pick it. If you already did it, then we're finished. I'm gonna give extra credit for anyone who did the pre-test and post-test. So please do it. My way to get more people to do it. It's not connected directly to your grades. You go course tools, there's quizzes, and there's a pre-test. There's a post-test by the end of the semester for comparing purposes. At the beginning of the Calc 3, normally we don't know a lot of it. So when you click on it, it's multiple choice. I think it's 6 or 7 multiple choice question about what we were supposed to learn in Calc 3. So if you did do so now, if some of the questions sounds really like different from what you expect, you can try your best effort, and then hopefully by the end of semester, you look at it in the test, you have better idea on how to calculate questions. Any question? If you had Calc 2 and Calc 3 in this school, you've probably seen similar stuff in Calc 2 and Calc 1. So there will be one quiz that's called pre-test, and there's another quiz by the end of the semester that's called post-test. The hope is that this data from these tests, from these quizzes, will offer us to collectively, as a whole, to determine whether the course is being designed as expected or is it not as expected. So we can kind of tell how it is. Any questions? please take the pretest because I think it due since here. It's due on the 25th. So if you haven't done it, you still have time. If you already did it, then don't worry about it. Yeah. Just want to mention that we once again I think we talked about it in the syllabus, but trying to catch the bases to make sure I didn't say we're doing it first. Just gonna try to. All right, we learned about vectors, so we're gonna have a practice question over the stuff that we did in 1.2. The last, the last part of the section 1.2 is about determining the unit vector. Try to work on it to get the right. The main idea for determining or calculate the unit vector is to find the magnitude and kind of figure out which page it is. Our unit vector is its definition. Unit vector is a vector that has magnitude equal to 1, but it's in the same direction as the vector we start with. So if this vector is already unit vector, you don't have to change it, meaning that if the vector magnitude equal to 1, that is the unit vector. If the vector magnitude is not 1, you might want to find that magnitude and divide it. So here we have the formula for determining the unit vector. So the first number 1, a unit vector in the direction of V is calculated by you take this V vector divided by the magnitude of V vector. That's how you can turn any vector into a unit vector. So vector U equal to 1 over magnitude of V multiplied by 1. So essentially the vector U and the vector V, they're proportional. All you are doing is multiplying vector V by a number. Magnitude of V is a number, so 1 over magnitude of V is still a number. It's really a number that we're multiplying to the V vector. So V vector multiplied by a number would be giving a vector that is the different lengths, different magnitude, but in the same direction. So U vector, V vector in the same direction, but U vector would have a magnitude that equals 1. That's what we wanted out of the unit vector. That is, unit vector will filter out the magnitude information because magnitude equal to 1, there's really no additional thing. So the unit vector contains solely the direction information of the vector V. Down here, we also mentioned something I talked about last week, that if you have a two-dimensional unit vector, then this unit vector's x value represents cosine theta, y value represents sin theta. So that's a two-dimensional unit vector. Now, if you have a three-dimensional unit vector, that's a little bit more complicated. You have to identify two angles. One of the angle is angle with relation to the z-axis. That angle is being called phi, right? And then the other angle is the angle between the projection of your vector onto the xy plane. That projection has a relation with x-axis and y-axis. The angle between that vector to the x-axis is our angle theta. I guess it makes more sense to draw a picture. Try to draw for the three-dimensional case. The one-dimensional case is easier to understand than the three-dimensional picture. We will be, remember pretest, take your pretest. We will be doing these when we're talking about spherical coordinate. So therefore, it's better that we actually have some understanding of it. So the two-dimensional case is, your two-dimensional coordinate system. And then we have this for x-axis, there's the y-axis. Right, and then here we're going to draw the vector. All right. So between the vector and the positive x-axis, you see an angle, this angle. And that's what we call theta. So let's see the terminal point of your vector is here. So draw a vertical line, now you're forming a triangle. So here is the x-axis, this is actually cosine, suppose this is a 1, unit vector here. So the radius or the length of the vector, want to draw a little arrow, that vector has a length of 1. Okay, and then so the x-axis will be a cosine theta, here is a sine theta. Now the y-axis of that point, this point, have a y value and cosine theta. Okay, so follow the idea that if you have a unit circle, then on the unit circle, any point will have a coordinate, x coordinate equal to cosine theta, y coordinate equal to sine theta. Any question? Are we okay with two-dimensional case? I posted a video today just so you will have a visual of how it is. It's in here. If you have time, you might want to watch this. So this is actually give you a really nice view of what's going on. And so for example, if that's a vector, then you can see the angle here. So the x equals 3, y equals 1, but obviously that length is not 1. That's not a unit vector, but we can turn this into a unit vector. That's another example. And then how do we turn unit vector? One of the ways you can do is to draw a unit circle. And the unit circle will be crossing. This is showing the vector, summation vector. So this is summation u plus v, because it's head to toe between u and v. So that's u plus v. And you can see from this, adding the x value. I is a unit vector in x direction, j is a unit vector in the y direction. We draw a unit circle for crossing the u, and there we have it, that's unit circle. So that little white arrow is the unit vector for the vector 3, 3, 1. So you see, if you write a component form of vector, it will be 3, 1 within the arrow bracket. But then if you write it into a vector form, this is kind of like, this is also the component form, but some of the textbook, especially physics book, will write it in that way. We will write the as the composition, a linear composition of these two vectors. So then, if I try to copy this down, so in this case, the I, I didn't copy that. This is the I. Okay. Basically, whenever you write I with arrow on top of it, it represents a 1, 0, 0. So I is a unit vector in the x direction. Now that's the component form of it. But writing the I would be a lot more convenient than writing 1, 0, 0. And then this vector is the one we call a J vector. It represented 0, 1, 0. So I vector and J vector are both in the xy plane. And then this is two-dimensional case, but the other vector we won't be able to draw here. It's called a K, IJK. K vector represent the vector 0, 0, 1. So basically 1, 0, 0, 0, 1, 0, and then 0, 0, 1. All three are unit vector in the axis direction, in the x direction, y direction, and z direction. So then this is an interesting example to illustrate how we turn a vector like u vector into a unit vector, and this kind of visually show how it's done. So there we have it. If you have a unit vector, then this unit vector if it's in 2 dimensions, then the x value is a cosine of the angle, the y value is the sine of the angle. Now about the 3-dimensional case, we also had that similar example in this video. I think I might want to draw my own picture. Let's do this 3-dimensional case. So let's see if you have an x-axis and y-axis and z-axis. Okay, and suppose you have this is a three-dimensional vector. Assuming we start vector from the origin and end it over here. So this vector itself will have an angle with the z-axis. This angle is what we call v. Okay. And then you can project this onto the xy plane. Let's say you have the intersection into the xy plane. So here so this is supposedly shorter than the original vector. Let's see. So if you turn the view around, this is your x-axis, this is your vector, this is the angle phi. That's the vector. You project onto the xy plane. This is the one. Like this. I'm trying to make it more two-dimensional view. This is a three-dimensional view. That's why it looks like a parallelogram with a triangle. So if this is a rho, which is a distance from the end point to the initial point of the vector, then we're forming a right triangle right here. So this side is opposite. Well, that's the phi. The phi. This side is opposite of the phi. So this side is rho times cosine phi. So the vertical one will be rho times sine phi. Adjacent side is cosine. I think I had it the other way. Opposite side is sine. So opposite of adjacent is sine. So sorry. So this is the phi rho times the radius times the sine of the angle. The adjacent side will be rho times cosine phi. So if you remove the distance information, so suppose rho equal to 1, and we don't have to worry about how long it is. So assuming that you already have a unit vector, then all these worry about distance is no longer necessary. So we think of this side as kind of removable. This is equal to 1. Distance equal to 1. If you got a unit vector, if this is already a unit vector, then in that case, that's already 1. So this is our angle phi. Parallel. This is parallel. So this is phi. That's phi. And this is the adjacent side, so cosine phi. So this point will have a z value of cosine phi, and this side will have a sine phi. That's what's in the right triangle if it's a two-dimensional case. But that means this length is cosine phi. And right here is the sine phi. And then sine phi is a projection of our three-dimensional one. This is 1. All right, onto the xy plane, there's our x, there's a y. Okay, now assuming this projection, this projection vector into the xy plane, have an angle with the x-axis. That one is theta. Okay, so now you look at what happened in the xy plane. There's x, y, and then here we have this is that one, and that's the sine phi. That's what's projected onto the xy plane. So sine, that was a phi. Okay, and over here we have, this is our angle theta. So you project this onto the x-axis. This is a sine phi cosine theta. Or another way of saying this, the sine phi is really the r, and this is the r into the xy plane, and then the vertical one is going to be r times sine theta. The horizontal one is r times cosine theta, and r sine phi. So that is r. That's the sine phi equals sine phi sine theta. So sine phi sine theta is the y value, and then sine phi cosine theta is the x value. Just try to explain. I mean, maybe it's a little awkward with all my drawing. All right, so essentially, this is where all these things coming from. The phi is the angle between the z-axis and your vector, if it's a unit vector. And then the cosine phi is the z value. We have to project this vector onto the z-axis. That's why we have a cosine, because it's the adjacent side to the angle phi. And then if you project this into the xy plane, you end up having a radius of sine phi. So that's the r. right? And then this radius you project it onto x-axis, which give you cosine theta. If you project this sine theta onto the y-axis, then you have r times sine theta or sine theta times sine theta. So that's how we can come together with the three-dimensional unit vector representation. So if you got a three-dimensional vector that is also a unit vector, in that case, then the x equal to sine theta cosine theta, y equal to sine theta sine theta, z equal to cosine theta. So then we will have a geometric understanding of why it happened and how they can be presented. I hope that kind of makes sense. Any question? We're not gonna apply this so soon, but later when we talk about spherical coordinate, we might come back to it, and then all these representations will make sense then. But right now we're just related to unit vector. Any question? The calculation of it isn't that difficult. We follow the number one. The unit vector is calculated by basically vector divided by the magnitude. So let's try. This is today's attendance question. We have a vector that started from point P, ended with point Q. P and Q are three-dimensional points, but PQ as a vector is a three-dimensional vector. We want to turn that vector into a unit vector. So that's what we do. And let's try to calculate it, see if you're able to calculate. First, vector PQ would be 5 minus 2, that's 3. So the first component is 3. And the second component is 2 minus 3, which is the y minus y. Times as -1. So 3, -1. Last one is -3 minus 1. It's -2. And then we divide it by the magnitude. That's supposed to be. It was be 14, sister. Okay. Let's finish calculating the vector and also determining the magnitude. Vector divided by the magnitude of the vector will get us the unit vector. Finish. You can submit your answer. Okay. But I think that's not. Yeah. So first we would take that's tells 5 minus 3, 5 minus 2 is 3. So the first component should be 3. So it's not -3. And then second is 2 minus 3. 2 minus 3 is -1. So it should be -1. It's not these two. So that's already all these two. And the last one is -3 minus 1. -2. So it should be, yeah. Okay. Right. Okay. And the magnitude is 14. You could try to calculate it.
Well, square root of 14.
Square root of 14. Thank you. That's a good point. I have 22 answers. Is that everyone in class? Raise your hand if you need more time. So you'll finish. So that should be the attendance. I think I got everybody. All right, the answer is supposed to be A. We show the graphic, and then that's all the answer that I have selected is all A. All right, that's it. If you came in a little later than when we were doing the particular question, feel free to stop after class so I know that you attended. Otherwise, this will be counted as our recording of the class attendance because everybody participated into this question together. All right, about the homework, we were supposed to finish 10.1 and 10.2 homework. Have you already finished? All right.
Sorry, I was just talking to myself there.
Do you have any question? Any question from the homework? So we're doing okay with the first and second sections? Okay, so we're gonna continue where we left. We were about to finish 1.2, with one thing that we haven't mentioned that is the one of the benefit of knowing the unit vector is giving us a direction. And one of the special relation between two vectors is what if they are parallel? If two vectors are parallel, they may or may not have the same length. If they're parallel, they were going in the same direction. And so if they're going in the same direction, then these two vectors are supposed to have the same unit vector, or at least have the same component except the sign. Maybe this vector goes this vector goes this. So the two vectors that are parallel, maybe parallel this way, but maybe parallel this way. Maybe one of them is going to the opposite direction, but they're still parallel nonetheless. So here we have number one says unit vector U1 and U2. They're parallel if U1 equal to U2 or U1 equal to negative U2. So that's about angle relation between unit vectors. Number two, if you have two separate vectors, and how do we determine they're parallel? One of the method is to find out their unit vector. So you turn both of them into unit vector. If these two unit vectors are identical, then the original vector are parallel. Now, if this unit vector are opposite of each other, then the original vector also will be parallel. So having parallel unit vector, meaning that the original vector are also parallel. Any question? Okay, so but there's a little bit of problem or a little bit of burden here. Every time we turn a vector into a unit vector, we have to find the magnitude. So dividing the magnitude is actual work. I often find that it's easier to look at the component of the vector to see if they're proportional. If the two vectors have proportional component, then they will be parallel. So it's easier than have to determine the easier than have to find the unit vector. So for example, if we get a vector like a 1, 2, 3, and that's our u vector. Okay, then you have a vector v that equal to 2, 4, 6. Okay, so you can see if you want to determine if these two vectors are parallel, one of the methods according to what we have on the board, you have to turn this into a unit vector. So this, if you turn this into a unit vector, will be 1 over root 1 square plus 2 square plus 3 square is 9. 14. So 1 over 14 and then 2 over root of 14, 3 over root of 14. That will be the unit vector from the first vector. Now the second one will be 2 over, this is going to be points. So all these number of points, so then it will be like 2 over, so it's kind of like this. And there's 4 over 2. 14 and then 6 over 2. So you will realize that they have identical unit vector. The unit vector from this vector and the unit vector from this vector, they're essentially the same thing. That's how we know they're parallel. But you can see if we have to go through the calculation of the unit vector conversion. But the other method will be, you can see if it's 1, 2, 3 for the first vector, 2, 4, 6 for the second vector, then 1 over 2 equal to 2 over 4 equals 3 over 6. So they are proportional, and the common proportion will be 1/2 between the two vectors. So the second vector is twice as long as the first vector, but they're parallel nonetheless. So using proportion is a lot quicker than to convert it into unit vector. Any question? We do occasionally have to figure out whether angles, whether vectors are parallel. Have our homework and see if that was the case. We similar issue about finding a unit vector, determining vector. A lot in this section. So section 2 does not have a lot of talk about parallel relation. And we might have one in the later sections about relations between vectors. Okay. So this is the one that I often find students have a lot of issue with because I have way too many questions. So this one. This is number 3 of 10.3. Maybe you haven't worked on it since I just assigned it today. And then the question involve these vector, like which pair are perpendicular, this is which pair are parallel. So since we're talking about parallel, I just work on number 2, then part B. All the other ones involve angle. To do that after we talk about 10.3. So let's focus on parallel relation. You can see A and B. They're definitely not parallel because the x component is 3 to -1. The y component is 1 to -3. So 3 over 1, 1 over 6, not proportional. And then the part C, AC, AB are not parallel at all. And then do we even have any that are parallel? I don't see any one of these pairs of parallel. That's 1, 1, 4. This is 1, 1, 1/3, 1/3. That's 3, 1, 1. That's 1, 3, 1. So none of them are parallel. I wonder if the student have different scenario. Let's look at. Okay, let me highlight this, just try to figure out which pair actually is parallel. Yeah. Okay, so this is one of these questions that are multiple relation. So in order to not miss any relation, we can make a chart of all the possible relation. Let me see. If you start with A, then you have relation between A and B, and then there's a relation between B and C. Then there's a relation between A and D. Okay. Okay. This one. There's a relation between A and B. So if we start with A, we have 4 pair relation. And then whether the relation between the two, they're either parallel, perpendicular, or somewhere in between. So those are the one we will be determined with study of 10.3. But right now we focus on parallel relation. So and then if you start with B, A and B is already there. It's just blood relation. So if you already have AB, we don't have to write down AB. So now there's BC and there's BD. Just trying to find a way to organize our sum. And then there's BG. And that's all possible pairs, possible relation between involving B. And then of course there's C. We already have BC, we already have AC, so it has to be CD. And then there's CG. The relation between vector C and vector G. And lastly, start with D, then there's G. Because all the other ones, we see A, B, AG, and PG, they're already there. So PG. So this is all. And I just want to find out which pair actually is parallel. So it's a lot easier to do it all together, but I'll just isolate the one that's parallel relation. So we'll see this one and this one is parallel. So you can see the coordinate for A is 3 is factor that goes 3, 1, and -1, right? And then what about G? That's A. And then G would be -3, -1, and then 1. Right? If you try to pair the ratio between the first component is 3 to the -3. And then there's 1 to the -1. And then -1 to 1. So essentially they all equal -1. They're the same ratio, right? So we know that A and G definitely is parallel. Oh, where was it? This one is parallel. And then you can see the other one, whether they are parallel or not, then B have one less component, B definitely is not parallel. And then there's AC also only have 2 components, not gonna be the case, and there AD. D has all positive, but A has 1 negative, that's never gonna be proportional. So there we have it. For involving A, there's only one pair parallel relation. Now we have BC. And that B will be like 1, -3, and then 0. And C will be -1 and 3, and then 0. Are these parallel? I think they are. So BC is parallel as well, and then BD, D has 3 components, B has 3 components, they are not going to be proportional. And then for CD, they're not parallel because C has 2 components, D has 3 components. CG, same reason, so there's no parallel. And then DG, D has all positive, but G has 2 negative. So here we have it. There's only 2 parallel relation among all the possible relations. Any question? All right. So when we actually answer this question, we may have to consider like, are these perpendicular? Are these 90 degrees? So the angle can be determined altogether for each one. Once we determine all the relation, we can answer all 5 questions at one sitting. So once you determine each relation. Right now, I'm just looking at parallel relation. The parallel one, as we mentioned, they were BC and AG. So we go A, G, right? The other one is B, C. That's the parallel one. Just want to give some help, some like my understanding of how can we quickly identify parallel vectors. Any question? We okay? All right, so if you wonder why are these ratios, like obviously 0 divided by 0 are not going to work, but we can see they're opposite. This is the opposite of each other. This is the opposite of each other. This is also opposite of each other. 0 is opposite. So you can think of if this is all 0, then they are both in the xy plane. So in the xy plane, so then they become 2-dimensional vectors. You can look at the 2-dimensional vector, they go -3, -1, 3, -1, and then 3, like this. Okay, that's this vector. Now 1, -3, it goes 1 unit to the right and 3 unit down, which like this. That's this vector. It would move 1 unit to the right and 3 unit down. So this one actually goes this way. And that one goes this way. So they are parallel, even though they're opposite direction. They're in the same, on the same line. Okay? Any question? So hopefully that gives us some parallel relation, how to determine vectors. And that ends I'm gonna skip the last question because it's really very much a physics question. I'll let you worry about it when you're in your physics. How many of you already have your physics? Yeah, okay. So, but we officially will come back. There are some of the physics class, so we're not avoiding it entirely. But this is a question that it's okay. We don't have to use vectors to solve it, even though we could if we would. So today we're gonna move on to section 3. Let's talk about dot products. I have already assigned the assignment. You already had your dot product. You have read about dot product before you may want to apply it. So in 10.3, we can learn about dot product and where do we need to apply dot product, or what kind of question can we answer with dot product. Right. So far we have learned how to add or subtract vectors. So dot product is one of the ways to multiply vectors. Okay, there is actually two different multiplication, two type of product. In mathematics, when we multiply numbers, quantity, vector, when we multiply, we call the result products. So for vectors, there are two products. One is called dot product, one is called cross product. We're gonna learn dot product in 10.3. We're gonna learn cross product in 10.4. So let's see how it's being defined. All right, definition for dot product. So let's say you have two vector. So here we define dot product for both two-dimensional case and three-dimensional case. The calculation are very similar between the two. Basically, to calculate dot product, you're going to take both of their first component, multiply it, and you're going to take both of their second component and multiply, and then you add it together. Basically, the dot product is summation of products for both vectors. Now, if you have two three-dimensional vectors, you're going to take their first component, multiply, add the second component, multiply, and then add with the third component, multiply. So again, it's a summation of multiplications for every pair of components. So the calculation for the dot product in 2-dimensional and 3-dimensional, they pretty much follow the same reasoning, same formula. Any questions? Okay, so let's try calculate it, and then we're gonna look at what's the usage of it. So here we have, let's calculate dot product for u dot v and calculate x dot y. We have all these vectors, the calculation, as long as we follow the definition, we should be okay. Well, the only problem is occasionally, like as human, we make small errors when we try to calculate this multiplication. Okay. Or maybe that's the case with me. I can't avoid 100% avoid small errors. So we will calculate u dot v by multiplying their component. Calculation for dot product. You're going to take the first component, so 1 times 3, which is 3. I add, and then we're going to take the second component. In this case, the second component 2 and negative. You multiply 2 with negative 1, you're going to get negative 2. So what we're looking at summation between 3 and negative 2 will be a 1. So the dot product between u and v is 1. Any questions so far? So we're going to do the same. We multiply x vector with v vector. Try to get this vector x dot vector y. Right, the calculation is, again, you'll follow every component. The first component multiply the first component, which is negative 2. That's when the x component is multiplied. And I'm going to take the second component, negative 2 multiplied by 0. Any number multiplied 0 equals 0. So there we have a 0 for the multiplication of the y component. The z component, we have 5 and 3. 5 times 3 is 15, so we add 15. So altogether, the total is 13. That's the dot. Any question? Right now here, now that we know how to calculate it, we kind of have to see how, what was the usage of it. Dot product, because there's multiplication, sometimes we multiply negative numbers, so there's no guarantee is the dot product positive, negative, or 0. So we get this idea that if you multiply two vectors, they end up being a 0, maybe there's a special reason or special meaning to it. And we can see One of the very typical situation is what if we have unit vector I multiplied by j, and I equal to the I vector is actually 1, 0, 0, right? And then the j vector is 0, 1, 0. So it's an axis. So when you multiply with dot product, you have 1 times 0 plus 0 times 1 plus 0 times 0. So it's really a 0 there. So we realize if we multiply the vector I dot j, we actually have 0. And what's the very obvious relation between I and j? I is along the x-axis and j is along the y-axis. These are perpendicular. So one of the special things that we can get from a dot product is if a dot product of any two vector, if the dot product equal to 0, it very well might be indicating this two vector are perpendicular to each other. I'm using that special notation, the vertical line and then followed by a horizontal line between the two vectors to indicate a perpendicular relation between two vectors. That's a lot easier saying I vector and j vector are perpendicular to each other. So it's a lot shorter than writing the sentences using symbol. So one of the nice thing about symbolic relation is that skip a lot of writing and have to be very big information. It's a notation. All right, so try to get more example on this. So that's what I'm going for, but let's go through the properties. So we talk about property when we're talking about summation of vectors in 1.2. Now we have similar property for dot product. Remember when we have u plus v, the vector summation, which equal to v plus u. So summation of vectors have as commutative property. Now, the number one indicating that dot product also have commutative property, that u dot v equal to v dot u. Second, we have distributive property that's saying that if you have u dot summation of the two vectors, then a equal to u dot v plus u dot w. So when do we consider or try to check for distributive property when we have two operations? So in this case, we have summation, we also have multiplication. We are combining them all. We're going to look at whether distributive property is true. So here, the number 3 is a distributive property on the right. Number 2 is distributive property on the left. Any question? Then we have number 4 is if you have a dot product and then you multiply a number, scalar, and then equal to when you multiply scalar to the vector and then to the dot product. So it's basically the same thing. The number 4 is indicating that we kind of have some kind of associative property within the numerical multiplication, and this is a vector multiplication. We differentiate them, but we also identify with their actual equal. Number 5 is about 0. Any vector multiplied by the 0 vector equal to 0. Number 6 is if you have a dot product dot with itself, it's actually equal to the magnitude squared. So number 6 is also one of the situations that we realize dot product has something to do with the magnitude of vector. This can be proved. We can actually write it out to say how that last one makes sense. Now we have a couple of examples here. For example, if we multiply the x vector with x vector, okay, so let's try to move this up. So So for example, if I multiply x dot x, so we have vector multiplied by scope. This dot product, this is what happened. So you can have 2, -2, and then 5 dot 2, -2, and then 5. When you're calculating dot product, you basically take the first component and multiply, that would be a 4. plus you're gonna take the second component and multiply. That's still gonna be 4 because -2 times -2 is 4. And then there's a 5 times 5, which is a 25 plus 25. So altogether, we have 33. But that's essentially the x squared, the y squared, and the z squared. Okay, so that's really the magnitude of x squared. So then the dot product of the vector with itself equal to the magnitude squared. And that's the mass formula that we have here. Right. Number 6 is also one of the properties that reminded us maybe dot product has something to do with the magnitude of each vector. So here we have a formula that we will be applying. So u dot v equal to a number. This number conveys two information. Number one, it has the magnitude of both vectors. So if you're multiplying these two, and maybe multiplying the magnitude of both vectors will be in there. Because we tried it already, u dot u has a magnitude times the magnitude of u in there. So therefore, u dot v should have magnitude of u and magnitude of v in there. So applying number or applying formula, you should be able to find out the magnitude of both vectors is involved in the dot product calculation. Another one is also equal to multiplication of cosine theta, which means that angle play a role in the calculation. So those two vectors are perpendicular to each other, even though they each have a magnitude equal to 1. Remember the I dot j. I have a magnitude equal to 1, j has a magnitude equal to 1. So how come I dot j equal to 0? The explanation that we had will be cosine 90 degrees equal to 0. So this the magnitude may equal to positive number, but the cosine theta might equal to 0 if the theta is 90 degrees. When the vectors are perpendicular to each other, what's causing the dot product equal to 0 is the cosine of the angle 0. All right, with this, we realize that dot product can be a really useful way to determine the angle between two vectors, because cosine theta is right in the value of the u dot v. So theta here is the angle between the two vectors. So then theta, since it's the angle between two vectors, theta is within 0 and 180 degrees. That is, here we have a vector, here we have another vector, u and v. So u and v are roughly in this very similar. Oh, I guess I should write on the computer, so it's easy to report. So this is really the main result of 1.3, that what kind of application can we apply to a dot product. So if you have a vector u and v, there are a couple of relations here. If u and v are roughly in the same direction, so here is u, here is v. So u and v had a acute angle between them. In this case, then cosine theta will be positive, and therefore the dot product, this will be positive. That's one situation. Or another situation will be when u and v are 90 degrees between them. So in this case, and here is the theta. So when theta is 90 degrees, then you can use your calculator to check cosine 90 degrees equal to 0, and therefore u dot v equal to 0. And that will be the second situation. And then last situation will be u is this, and v is this. U is here, and v is this. That's basically kind of like you go that way, I go that way. We are going to roughly opposite direction. So they're not 100 degrees between the two vectors, but they seem to be deviated. Like the acute angle, u and v have an acute angle between them, even though they may not be exactly 0 degrees between them. When the angle theta equal to 0, that's when they're in the same direction. That's when cosine theta equal cosine 0 equal to 1. That's when that's equal to 1. Okay, that's when they are going exactly in the same direction. But when the angle is acute, they're roughly in the same direction. Now over here, if the angle theta is obtuse, right? Like 0 to pi, they're in the acute angle. In this case, then the cosine theta is negative. Okay, if cosine theta is negative, and then we will see that these are all positive, and cosine theta alone is negative, and therefore u dot v is negative. So the dot product will be negative. Okay, and this gives us the idea. If you finish calculating dot product and dot product end up being positive, that's really indicating u and v are roughly in the same direction. If the dot product equal to 0, that indicating they're 90 degrees to each other. If the dot product is negative, they're roughly like opposite way. So that's some of the quick way to tell what kind of relation the two vector has. And that's why in the question that we were talking about, this question, right? The question saying, are these two, which one of these vectors are perpendicular to each other? Which one is indicating that we have an angle less than 90 degrees? Which pair has an angle more than 90 degrees between them? So to answer A, C, D, all you have to do is calculate their dot product. Then we're all set. Any question? We realize if they're parallel, then it will be similar to this one or that one. So there may be some overlapping. That's why parallel is one of the singular relation that's not explained 100% by the dot product. So I would say ACB can be quickly determined with the dot product calculation. Let's try to finish what we started here. Okay, so with that, that's a better picture than what I was drawing. So dot product positive, that's angle, acute angle between the two vectors. Dot product equal to 0, 90 degree. Dot product negative, that's a choose angle between them. You might ask, why don't we have angle higher than 180? You see this angle is higher than 180. The thing is, we only focus on the one that's lower than 1. So two vector this way, we never look at the angle on this direction. We only look at angle on this direction. Okay, so kind of like that. That's acute angle. But what about the other one on the outside? So that's not the same. Where we look for is with respect to angles. All right, so here's one of the question. The question said, let's calculate the angle between vector. Let's calculate angle alpha, beta, and theta. Alpha is the angle between u and v, and then beta in the picture. Beta is the angle between w and v. All these vectors are two-dimensional vectors, so it's easy to draw them. So you see that u is 3, 1. We go 3 and 1. That's u. And then the v is negative 2, 6. You go negative 2 and then 6. That's v. W is negative 4, 3. Negative 4 on the x-axis and 3 on the y-axis. There we have a terminal point connecting them. We have our vector. So UVW has already been drawing the picture. Therefore, it's easy to draw alpha and beta. And you can see the theta. This is two-dimensional. So alpha plus beta is theta. So in a way, because this is two-dimensional, then calculation for the three angle means we could calculate alpha and beta added together. There we have theta. So we can try to calculate this angle. All right. So how do we calculate angle there? We go from this equation. So we're going to calculate angle between the two vectors. We see that cosine theta will be the dot product divided by the magnitude. So that's really a byproduct of these formulas. Come up with the formula and now we apply it. All right, so according to this equation, right, then we can draw equivalent equation, which goes like this: cosine theta, sine of theta. We divide both sides by the magnitude multiplication. So cosine theta is equal to here, the left side of the equation divided by u dot v divided by, well, all we have to do is move this one remove this, and then cosine will be by itself. So we divide both sides of the equation by this. Okay, so cosine theta equal to u dot v divided by magnitude of u times magnitude of v. And basically u dot v is a number. So dot product really is a way to turn two vector into a single number. Remember, number and vector are not the same thing. And then the magnitude is a number, and then magnitude is a number. So we take these three numbers and do this division thing. And then we do that. We're gonna apply that formula to this question. Right there. Let's see. I'll be over that. Good question. Here's our formula. By that formula. So let's see, how do we calculate alpha? Alpha is angle between u and v, and here is u and v. So cosine alpha is equal to cosine alpha is equal to, and it's angle between u and v. So it's going to be calculated by u dot v divided by magnitude of u and magnitude of v. That will be a calculation of it. Let's calculate it one by one. So first, it's a dot product u dot v is equal to 300 negative 6. That's negative 6. Oh, 1 times 6, that's 6, which is really equal to 0, right? So there's going to be numerator of the calculation equal to 0. That means alpha equal to what? Alpha is 90 degrees, right? Because the cosine equal to 0. So the angle has to be 90 degrees. Are we okay? For alpha? We don't have to calculate the denominator. The denominator is positive. Numerator equal to 0, and 0 divided by any positive number is 0. Are we okay for the calculation for alpha? Any question? We're gonna move on to beta and calculate. Let's go calculate cosine beta. Once we find the cosine, we'll do inverse cosine to find the cosine beta is equal to beta is angle between v and w. So it's v dot w. W dot v, v dot w, the same thing. So divided by magnitude of v vector times magnitude of w vector. I was going to calculate all three, and then now it was 0, so that's why I stopped. All right, now w dot v, v dot w, the same, equal to, this is a w, that was a v, negative 2 times negative 4 is 8. Plus 6 times 3, that's 18. So that's 26. Okay, the number magnitude of w is equal to square root of 4, negative 2 squared is 4, and then 6 squared is 36. So that's root of 40. I need a little bit more space. Let me get rid of this. And then the magnitude of v, which equal to square root. Do backward. That's magnitude of v already. It's magnitude of w. It's like mess up w and v. So magnitude of w is this. So it's 4 squared is 16. And then 3 squared is 9. That's really 5. That was magnitude of v there. All right, so the calculation for cosine beta, follow that formula. We will have 26 divided by 5 multiplied by root of 40. And that's cosine beta. All right, so if you want to know the actual beta, you have to do inverse cosine. So beta equal to cosine inverse of 26 over 5 times root of 40. That you need a calculator that has inverse cosine. Are you okay so far? So maybe the writing part. This is a basic calculation. When this is ready, we apply the formula and calculate cosine. Let me grab a calculator and calculate this. If our cosine or cosine inverse of 26 divided by a multiplication between 5 multiplied by square root of 40. So the rating measure, we multiply this by 180 to get our cosine value. So that's really measure. I'm multiplying 180 to convert it into a degree measure. So it's not right. That's definitely. That's the reading measure. Wait, how do we convert reading to degree? Multiply by 180, right? Right? Was that wrong? Did you guys finish try to calculate 26 over 5 times? I'm confused. Is there any calculation error in here?
Yeah,
Yes.
multiply 1.180 and divide by 5, and it's gonna be 35 degrees from the our cosine of beta.
So is the cosine beta wrong? Is there?
No, I say that when we convert radians, the degrees are multiplied by 180, but we also divide by 5.
Right, 180 divided by pi, my conversion was wrong. Thank you. Yes, so I was like, I must have done something, let's say. Okay, so this reading measure is right, and then we multiply the 180 over pi converted to degree. So that's the degree measure. Oops. Okay, so because I got 90 degree already, so I want to convert the beta to a degree measure. So then the degree measure is 34.7 degrees. So make it one. A degree measure is 34.7 degrees. Degree notation. So we have alpha equal to 90 and beta equal to 34.7. So then let's say theta. Theta is summation between alpha and beta. So theta is actually 124.7 degrees. There. We finish calculating alpha, beta, and theta. That is the textbook solution. So you can see alpha is 90 degrees and then beta is the reading measure is 0.6055. And then we have to convert it to degree, it's 34.7. And then theta can also be calculated the same way. Theta is the angle between U and W. You can do U dot W over magnitude of U multiplied by magnitude of W. And then we can find the reading, the cosine of the angle theta. And you do inverse cosine to find the angle. It should be 124.7. But then you can see from the visualization of it that 90 degree plus the 34.7 degrees is also 1.4 degree. So we can have two different ways to calculate theta. That's the whole solution to this example. Any question? We okay? So this is applying the dot results to determine things. So that also brings out one of the fact that dot product is really useful for determining angles between vectors. There's a similar example. All right, so now that we had the angle relation, we're going to define some new terminology. This is a word orthogonal. Have you heard of this word before? So this is about vectors. When two vectors are having a dot product equal to 0, we call them being orthogonal. So in a way, when vectors are perpendicular, they're being considered orthogonal. Any question? terminology, the word orthogonal has been defined when the delta equals 0. Right, so if we have time, let's talk about when orthogonal projection. So this is trying to, one of the ways to decompose a vector. So here we have two vectors, vector u and vector v. So we can think of the relation between u and v. And we've been talking about maybe u and v are in very similar direction, but not exactly identical to each other. For example, I'll show you another one. Well, there's a picture already on the screen. We'll just use that one. Picture. Okay, so suppose we have two vectors. They seem to be following along the same direction. So you can see we can see u is going this way, v is going this way, right? So they are in slightly different direction, but mostly the same direction. So we might want to think about how much of u is following the v. Okay, and then so in a way we could think of u as the summation of two vectors. So you can think of maybe u can be considered as this is one vector, one part of the u, and this is another part of the u. Then u would be the diagonal vector in that. Well, this is actually a rectangle, right? So in this rectangle, the u is a diagonal. So in a way, according to our summation of vector relation, u is the summation of this vector and that vector. So we call the perpendicular one. This is actually perpendicular to v. So this is what we call the vector. So you can think of u as summation of two vectors. U equal to z plus w. U equal to summation of this two vector. So w is part of the u vector that follow along with the v vector. Now z is part of the u that is totally different from the v vector. So it's going to a perpendicular relation, which is exactly not in relation to z to be in any way. So we're decomposing this vector u into the perpendicular component and the parallel component or identical component to the v. So we're giving this w a special word. We're calling u is a projection of u vector onto v. So u is part of the v. W is part of the u that is in the same direction as v. Any question? So what we're doing is trying to figure out a way to write out the vector z and write out the vector w. Suppose u and v is given. So how do we calculate it? We follow what we did with today with dot product. So what we're going to do is one thing we should remember is that the w would be a vector that is in the same direction as v. So w is going this way, v is in this way. So in a way, w has to be part of the v or a scalar of the v. All you have to do is change the w, change to the v, sorry. The w and v are in the same directions. They're basically part of the same vector. So w equal to v vector multiplied by a number. So in this sense, all you have to do is take the v vector multiplied by a tricky number. So then the w is also part of the u. Okay. So what we're going to do is follow the triangular relation. What you can see is w has to have the same direction as v, but at the same time, w has to be, the length of w has to follow this triangle. So magnitude of v and magnitude of w is fitting in a triangle because w is, after all, part of the u. So w gotta have the magnitude of w has to follow the right triangle. I was going to try to make a copy of this. Have enough time. difficult time. So essentially what happened is this is a right triangle. This is really a right triangle because that was perpendicular. This is really a square. That was theta. So W is on this side. Magnitude of W would also be on that side. So you can, this is a magnitude of U, the length of U, length of W, if you're fitting in this triangle here. So if you take the magnitude of W, which is adjacent side of theta, this is right triangle. Adjacent over hypotenuse, hypotenuse will be the magnitude of U, which then equal to cosine theta. It's cosine theta in the right triangle, cosine theta equal adjacent over hypotenuse. So magnitude of W over magnitude of U equal cosine theta. Therefore, magnitude of W equal to magnitude of U times cosine theta. This is a follow along with the definition of cosine. So there we have that relation. So why are we doing this? Because W equal to C. How are we gonna try to do is come up with a formula for W. So W should equal to one of the component is how long W is, and then this is essentially the magnitude of W. So it's the magnitude of W. Vector equal the magnitude multiplied by the direction of that vector. Direction of W vector is supposed to be in the same direction as V. So how we get V into a unit vector is V vector divided by magnitude of V vector. So this part is converting the vector V into a unit vector. This part is trying to find a way to figure out the right length of W. And this is really how we come up with the formula. All right, from this, we're gonna continue on to find the formula for W. And then cosine theta, theta is angle between U and V. So cosine theta is U dot V over magnitude U times magnitude V. By now, over here, we already have the formula for W, but we might want to simplify this a little. So this is what we have when everything is U and V are already given. So assuming magnitude of U and V is a problem. So then we cancel some of the common factors. So here we're gonna cancel this in magnitude, cancel that magnitude. All right, and then these two together, this two multiplied together, it's a square. So now we have this one. So that will be our formula. We will be applying later as a formula for projection onto vector. So the W equal to a single number multiplied by V, because W is along the same direction as V. So U is a vector, W vector, it is a vector, V vector multiplied by a single number. This number is actually a ratio dependent to the delta divided by the magnitude of V. I don't know. It's kind of my awkward way trying to explain that formula of the projection. This projection formula is useful for decomposing any vector into where do we go with the same direction, where do we go in the perpendicular direction. It will be useful for when in physics, sometimes we do want to decomposing a vector to identify which part of it is going this way, which part of it is going in a perpendicular direction. And that'll be for today. We're going to try to practice more questions tomorrow, but today we're just going through the formula there. And then we'll try to apply the formula. I'll see you tomorrow. Thank you. Yeah, it's just my. Still online. We should be able to complete those of the question. It was supposed to be It's supposed to be A. Are you still there, English? Oh, what was your question? Can you attend online?
I don't know, that's what it's to us, but you will. So I'll make sure to watch all the videos.
Okay. Yeah, you can also watch the video and look at the attendance questions. If you submit the attendance solution to the attendance question to me, so I know that you did watch the recording, yeah, could double add your participation. That way you won't not be on the absolute.
Okay, all right, thank you so much.
Sorry, thank you. I see that you submitted your answer. Thank you. Yes, you say this way every single time they're using the same link. So next time you attend virtually, you'll be using the same. Each time it's the same. So bookmark this, you won't have to ask for the link again. Thank you. So I'm gonna log out. Bye.